In this video, we're going to find the greatest common factor between numbers and then see how we can extend that knowledge and apply it to polynomials. So to start off, let's just look at two numbers here. Let's say we have 18 and 27. So what we're going to do is use the factor tree method, and we're going to split this into 9 times 2, and then split this one into 3 times 3. And so we'll circle our prime factors, and then we're going to repeat the process for 27. So over here we're going to have 9 times 3 is 27, and then 3 times 3 is 9. Okay, now the greatest common factor is simply the product of the common prime factors. It's kind of a mouthful, but all it means is that if we drew a line here, we want to look for matches on either side of the line. So we have a 3 here, 3 here, 3 here, a 3 here, and then these we just ignore because they don't have a match on the other side of the line. Then to find the GCF, we just multiply the ones that we found. So here we're going to do 3 times 3 equals 9. So our GCF is equal to 9. Alright, let's do a slightly more involved example. Let's say we have three numbers, 20, 50, and 120. So we want to find the greatest common factor here. We're going to factor this one into 5 and 4, and then 2 and 2. So all of these numbers are prime. And we'll split this one into 5 and 10, and then 5 and 2. And then one more. Let's do 10 and 12, 5 and 2, 6 and 2, and 3. Should not have circled that. And then 3 and 2. Okay, so in this case, it's really the same process, but now we just need to find a match in all three of these numbers. So let me grab a bigger marker here. Okay, so we have a 5, a 5, and a 5. Then I see a 2, and a 2, and a 2. And I think that's it, because we don't find a 2 here, we don't find a 5 here, and we don't find a 5 here. So yeah, we're kind of at the end of the line, but we found two numbers, so our GCF is going to be equal to 5 times 2 equals 10. We're getting pretty good at factoring numbers and finding the greatest common factor between two or three numbers. So now we want to apply this knowledge to polynomials. So let's say we have a polynomial 7x plus 21. This entire thing is a polynomial, and each of these individual parts is referred to as a monomial. So when we have something that looks like this, we want to extract the coefficients of each monomial, 7 and 21, and then we want to factor them, just like we were doing before, using the factor tree. So 7 is a prime number, so we just circle it, and then 21 can be broken up into 7 and 3. 7 times 3 is 21. And then to find the greatest common factor, we just find the common factors between the two. If there was more than one, we would multiply them. In this case, there's only one, so the GCF is 7. So far, so good. When we have the GCF, then we can rewrite this polynomial with the GCF out front. So we have 7 times something, and this something you can figure out by dividing each monomial by the GCF. So let's do that now. 7x over 7 is just equal to x, and 21 over 7 is equal to 3. So this is the new polynomial, and that's factored. You can verify that it's right by multiplying it back out. So 7x plus 21, that checks out. Of course, this is a very simple problem, so it might seem obvious to you, but in the future, if it's a longer problem, the same sort of distribution method for checking will work. Okay, now let's look at another problem, this time a little bit more difficult. Say we have 8x squared times y plus 12xy squared. In this case, we're going to do the same thing to start. We're going to extract the coefficients and factor them. 2 times 2 is 4. So we have 2, 2, 2. Then on the right side, we'll have 6 times 2 is 12. And then 3 times 2 is 6. Now let's find the common factors. We have a 2 and a 2, 2, and a 2. So our GCF in this case is going to be 4. And these ones we ignore because there's no match. Alright, so far everything is the same as the last time. But now we get to the tricky part. We have x's and y's here. So how you can think about this is actually 8x times x times y. So I'm just taking this number and kind of expanding it into this. And then we have 12 times x, y, y. Now we can use our GCF and write it up front. But what we need to do is figure out how many x's and how many y's we can take from each monomial. We have to take the same amount from each one in order to put it out front. So for the x's, we're going to take 1x here and 1x here. And that's going to be it for the x's. And then we're going to take 1y here and 1y here. So we're going to have 4xy out front. And we can't take any more because, for one, there's no more y's over here and there's no more x's over here. Now what we can do is divide. See if I can get rid of some of these circles because they're in the way. Is we're going to divide each of these monomials by the thing we have up front. So 4xy, then 12xyy over 4xy. And what we discover is that x's cancel. This becomes a 2. And so our first term is going to be 2x plus, we can do some more canceling on the right side. This x cancels, y cancels. 12 over 4, this becomes 3. And so our second term is 3y. Not too bad. Alright, let's run through one more. GCF problems are definitely the easiest of all factoring problems. It's really a matter of just kind of finding what things go into all elements and then pulling them out. And you're not always going to write out all of the factors every time. Soon you'll just get really quick at doing it in your head. Okay, so in this case, I will still write it out. So we have 36 on this side and a 60 over here. And we're going to break this up into 12 and 3. Circle that. This is 3 and 4. Circle that. And then 2 and 2. And over here, we have a 12 and 5. Circle the 5. We have a 6 and a 2. And then a 3 and a 2. So looking for the common factors, we have 3 here, 3 here, 2 here, 2 here, and another 2. And no matches for the 3s or the 5s. So our GCF is equal to 3 times 2 times 2, which is equal to 12. Let's see if I can get just this. Okay, not perfect, but not terrible. Okay, so now what we're going to do is the same thing we did before. We're going to pull the GCF out front, and then we can rewrite this as x, 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 y, y, minus 60, x, 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 y, y, y. And you're really not going to do this on paper. What you're really going to do is just look at these numbers up top, and that's how you'll know how many values are there. But for the sake of representing it visually, this is a pretty fair way to do it. Now, let's see how many x's we can get from each one. X, x, x. So there's 3, and then we have no more x's over here. So we're going to have x to the third out front. And now let's do the same thing for the y's. We have 1y, 2y, and then no more y, so we stop. So this becomes y squared. Put our parentheses here, and then let's divide each side by what we have out front. So let me get rid of the circles again. This was self-inflicted. Okay, goodbye. Now let's divide this by 12 times x, x, x. And so I'm just rewriting this with all the x's and y's laid out. We'll do the same thing over here, just because it is very satisfying to cancel out values. So now let's see what we get. Gone, 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 gone. And then this becomes a 3. So our first term is just 3. Nice. And we're going to do a minus. And then we have that's gone, that's gone, that's gone, that's gone, that's gone, that's gone. So we have an x and y on top, and then we divide this. This becomes a 5. And so our second term is minus 5xy. So that doesn't look too bad. So now let's just, this is where the double check comes in handy. We can do this, 36x cubed y squared minus 60x to the fourth y to the third. And for sure that matches up. Sweet.